Uh, Good morning. Today I will present plausible ceiling for gradual parametricity, which is a joint work with Matthias Toro, Rick Danter, and Dominic de Vries. This work revisited gradual parametricity with the familiar syntax of System F. We aim to design a target language called Funky with parametric polymorphism and gradual typing, while preserving the two main properties of this feature, parametricity and graduality, and allowing the translation from a source gradual language to this target language. First, I will explain some concepts like parametric polymorphism in System F and parametricity, gradual typing, and graduality, some challenges in combining these features, and finally, our proposal of plausible ceilings and some perspective. Um, Parametric polymorphism enables the generic definition of functions and types. System F formalized this notion with introduction of universal types and a mechanism for abstracting types. For instance, this program instantiates the type abstraction for the identity function with type for all x, x arrow x to the type in and the value 42, returning the same value 42. A fundamental semantic property of polymorphic types is relational parametricity. And the idea of this property is that a polymorphic expression behaves uniformly for all possible instantiations. And an essential application of parametricity is that from the type of a polymorphic function, we can derive theorems, and every function of the same type satisfies the same theorem, hence the name free theorem. For instance, if we have the function f and we don't know its implementation, but we know that its type is for all x, x arrow x, then by parametricity, we know that must behave like the identity function. Therefore, if we apply f to int and to a type and a value of the same type, we should get back the same value. Also, we know that most languages today have either static or dynamic typing, and both have complementary strengths. Gradual typing tries to integrate the best of these two worlds, supporting the smooth transition between static and dynamic type checking. It's about programming with imprecise type, with introduction of the node type, which may represent any type, and allowing a programmer to write program with all type information, like the type in or bool, without any type information with a type unknown, or an incremental migration in either direction. Here, for example, the type in arrow bool is more precise than in arrow unknown, and so on. And gradual typing, what it does is the best effort optimistic static checking backed by dynamic checking, and this optimism is captured by relaxing type relation. For instance, consistency is the realization of type quality. Here, for example, the type in arrow unknown is consistent with unknown arrow bool, but not with bool arrow no, because in and bool are not consistent. There are some desirous property in gradual typing, but in this work we focus on the dynamic gradual guarantee, also called graduality, because it's the most challenging property for gradual parametricity. Graduality requires that if a programmer makes the annotation less precise in a well-typed program that runs correctly, then it will continue to do. For instance, the first program defined the variable x with type in and the value 42, and then apply a function that adds 1 to its argument, returning 43. The second program is very similar, it's only changed the annotation of the variable x to null, making this program less precise. So by graduality, this program also must reduce to 43. So graduality ensures that reduction is monotone with respect to type imprecision. But why is gradual parametricity challenging? First, it has been shown that without taking precautions, parametricity could be violated in a gradual language. Suppose that we have a function f with type for all x, x arrow x. Then by parametricity, these functions must behave like the identity function or fails in a gradual language. An implementation for f could be this function that adds 1 to its argument. Note that this function is well typed because of the description to the node type in the parameter x. However, it's not a correct implementation for the type for all x, x arrow x, because we can get different behaviors for different type instantiation, and of course because it doesn't behave like the identity function. So if we apply f to a type and a value, it must raise a runtime error to preserve parametricity. But if we follow a naive reduction approach like in system F, this program will reduce to 43, violating parametricity. So tracking type safety at runtime is not enough. We need to introduce a new mechanism. Most gradual parametric languages use global dynamic sealing mechanism to prevent this violation. For that, the operational semantics is extended with a global store to store fresh type name or seals that are generated when type applications occur. For instance, in this program, we generate the seal alpha when we apply the function f to int, which is equivalent to apply f to alpha and a seal version of the value 42 in order to protect it. Then we substitute this seal value in the body of the polymorphic function, and a parametricity violation is detected when we try to add 1 to this seal value, yielding a runtime error. But this mechanism itself only resolves some of the challenges of gradual parametricity. One of the most challenging or complex problems is to decide whether to seal or not to seal when imprecise types are involved. For instance, these programs are very similar. Both polymorphic functions has a parameter of type unknown, but the first function ascribed its parameter to the type x, and the second one to the type int. Therefore, the first polymorphic function must behave like the identity function, behaving the same for all possible instantiations. So the argument should be sealed in order to be protected, while the second function should only work for argument of type int, so the argument should not be sealed. Also, by graduality, this program must behave like this more precise static version. Note that in the first version, we changed the type annotation for the parameter x from unknown to x, representing that unknown stands for x. And in the second example, we changed unknown to int, meaning that unknown stands for int. We know that the static program reduced to 42 because they are system F program. Therefore, by graduality, the less precise version also must reduce to 42, but as we said before, in different way. The first program should see the argument to protect it in the body of the polymorphic function, and then unseal it, returning 42, while the second program should not see the argument, also returning 42. Most gradual parametric languages base the decision to seal or not to seal according to the function to be applied, to the type of the function to be applied, and this is type-driven sealing. For example, if we have a polymorphic function g with a parameter of type unknown, we have to decide whether to seal or not to seal the argument, because this unknown can stand for a type variable x or any type like int. But both decisions break graduality. If we decide always seal the argument, then the second example breaks graduality because it fails. Otherwise, if we don't seal the argument, then the first example does. Another approach is proposed by the language PolyG, which we call term-driven sealing. Here, the programmer inserts sealing and unsealing manually. For instance, this is a valid syntactic program in PolyG and also in System F, but it's not well-typed in PolyG. To obtain the expected behavior from the identity function, we have to seal the argument, and if we want to use the result, we have to unseal it first, returning 42. So the syntax of PolyG departs from System F, and also it's worth noting that a translation from a counterpart of Gradual System F to a language like PolyG have to face or to resolve the same problem to decide whether to seal or not to seal. So to address this problem, we propose plausible sealing as a new intermediate language mechanism that allows postponing this decision at runtime. Let's see how plausible sealing works informally. So if we have a polymorphic function that has a parameter of type no, instead of decide whether to seal or not to seal when we apply the function, we generate maybe sealed forms statically. So this program is equivalent to apply the polymorphic function to int and a maybe sealed version of the value 42. These maybe sealed forms allows value to be simultaneously sealed and not sealed, being plausible to be sealed but not mandatory. And the decision is postponed and is dynamically taken when we have enough information about how the value is used. For example, this previous example that instantiates the imprecise identity function would be equivalent to apply the polymorphic function to int and a maybe sealed version of the value 42. Then we substitute the maybe sealed value in the body of the function. And since an unsealing is going to be done because of the tie ascription to the type variable x, we use the maybe sealed value as a sealed value, returning 42 as expected. The second program, which only works for argument of type int, reducing a similar way, we apply the polymorphic function to int, and again a maybe sealed version of the value 42. We substitute in the body of the function, and since no unsealing happens here, we use the maybe sealed value as no seal, returning 42. So to generate these maybe sealed forms, we take into account the type variables that the unknown type has in its scope. For this reason, we decorate the unknown type with these type variables. For example, here in this program, we decorate the unknown type with the type variable x. It's only variable in scope. So we can only seal or unseal with x. This decoration of the unknown type is essential to feature lexical-scoped sealing rather than global sealing, and also is useful to generate maybe sealed forms only when necessary, and this is when imprecise types are involved. For example, when a polymorphic function has a completely static type, we don't need to generate maybe sealed forms, in contrast to other proposals. This version of the previous program runs in a similar ways as it does in System F without generating maybe sealed forms. But why is relevant this lexical scope sealing? First is a novel approach. All other proposals use global sealing. Second is simplify the static and dynamic semantics of the gradual language, because we don't need to use global store, and also because seals are not generated at runtime but statically. Also, it allows us to establish a standard formulation of parametricity. To establish parametricity, we use logical relations. I will not go into details here, but I only want to highlight that our proposal supports a formulation of parametricity where semantics type are tracked in lexical environments similar to Reynolds definitions. The only unusual case is the definition of the type unknown, which is expected for any gradual language. Also, we conjecture that a lexical scope sealing allows us to satisfy a new proposed criterion for gradual typing called fully abstract embedding. This criterion requires that the embedding from the static to the gradual language must be fully abstract, and is relevant because it ensures the preservation of semantics property in the gradual language, such as in our case, parametricity. These criteria have been disapproved for previous proposals by counterexample, but in this work we shows that these counterexample don't apply to our language. Something that the lexical scope sealing don't allow us is the embedding of the cryptographic lambda calculus, which is an extension of the lambda calculus with sealing primitive. And this is because the gradual language have to be based on a global sealing mechanism. For instance, the gradual polymorphic language GSF can embed the cryptographic lambda calculus because it's based on global sealing. This example shows another flexibility of plausible ceiling and its lexical scope, making possible to support multiple ceiling behaviors. For here we apply a polymorphic function to two types and a value, returning a pair where the first and the second components are the same value but with different types, x and y respectively. So we decorate the unknown type with the variable in scope x and y. Then we can the argument of the function 42 is treated as plausible seal to both x and y, but we use each component of the pair in different way. The first component is unsealed by the type variable x, while the second component of the pair is unsealed by the type variable y, returning this pair. It is important to mention that this example don't work in other proposals because we have to decide whether to seal with x or y in advance. To study plausible sealing, we propose the intermediate gradual language Funky, which can be used as a target language of different source language. Funky is an evidence-based language, making an analogy evidence are similar to CAS in a CAS calculus. We propose a new representation for evidence as set of span, based on category theory for a proof-relevant notion of type precision, fully satisfying parametricity and graduality. Also, we propose the source language func with the familiar syntax of SysNF, which elaborates to Funky. And this elaboration is in charge of introducing these maybe sealed forms, which are nothing more than evidence. It is important to mention that we develop our approach in a simplified settings where instantiations are restricted to base types and type variables. And this is in order to simplify the method theory. So how does an evidence-based language work? The typing derivation of a gradual language has a consistent judgment where evidence are local justification of why this judgment holds. The evaluation of a program proceeds by combining evidence through consistent transitivity. If consistent transitivity is defined, then it's justified the transitivity step of reduction. Otherwise, the evaluation fails with a runtime error. In simple settings, an evidence can be represented as a type G, justifying that G1 is consistent with G2. To calculate G, initially we calculate G as the mid between both types in the consistent judgment. And always G is more precise than G1 and more precise than G2. But by previous work, we know that this representation of the evidence is not sufficient for gradual parametricity. So we propose a new one. First, we add a proof term to the type precision relation in order to justify why the precision relation holds, because a type can be more precise than another type for different reasons. So the precision judgment now is represented as the more precise type G and the two proof terms C1 and C2. And we call this triplet span because it's similar to the category of span. For instance, here we have an span that justifies that in is consistent with null, decorated with the variable x that was instantiated at the type int. On the left, we have a reflexive proof that justifies that in is more precise than int. And on the right, we have a proof term that justifies that in is more precise than this unknown. This is another example of a span that justifies the same precision consistent judgment. But on the right, we have a new proof term, inject int, that justifies that in is more precise than the same unknown. Note that we have different precision terms, inject x and inject in, for the same precision judgment, but inject x represent that unknown stand for x instantiated at int, and unknown and inject in represent that unknown stand for int. The last step in the evidence representation is to generalize evidence as set of span, and this is in order to support Mebicil forms. Here, this Mebicil evidence is formed by the two previous span, where the first span is a ceiling span, and the second one is a no ceiling span. To support the transitivity of precision judgment, we define the composition of proof term. For instance, if we have a proof term C1 that justifies that G1 is more precise than G, and a proof term C2 that justifies that G is more precise than G2, we can always combine proof term, obtaining a new proof term C that justifies that G1 is more precise than G2. To define a consistent transitivity between evidence, which are set of spans, we have to apply consistent transitivity between all possible combinations of spans between both evidence. If the resulting set is the empty set, then consistent transitivity fails, meaning a runtime type error. Consistent transitivity between a span is more interesting. For instance, if we have a ceiling span and an unsealed span, to combine them, we have to first calculate the pullback between a span, ensuring that the middle diagram commute. And this is that the combination of proof term on the left and on the right is the same. In this case, inject X. This pullback operator is partial because it's not always defined. If the pullback is not defined, then consistent transitivity between span fails. The last step in the is the combination of the proof term on the extreme, obtaining a new evidence that justifies that int is more precise than int. As we say before, funky, our proposals satisfy parametricity, which allow us to establish free theorems. For instance, we can write a free theorem for a function of type f, for a function of type for all x and no arrow x, that say that must behave like the identity functions or fails or diverge. What else we can find in this work? First, we explain a graduality restriction on type applications for the source language func. Also, we mechanize key lemmas in Agda, and we develop an interactive prototype with illustrative examples. As perspective, we want to stand funky with instantiations at any type and remove func's graduality restriction for type applications. Also explore if funky satisfy the fully abstract embedding criterion, and if plausible ceiling can be reusable in other settings such as security type or probabilistic languages. As conclusion in this work, we propose plausible ceiling based on a proof-relevant notion of type precision, lexical-scoped ceiling, and a representation of evidence inspired by the category of span. Thank you.
Plenty of time for questions.
Hi, thanks for the nice talk. Is there ever a situation where a maybe sealed value in gets duplicated and is turned into a seal in one circumstance and not turned into a seal in another? So can you get kind of two different paths for a value?
Yes, could be. Maybe seal value can be used, for example, in some part of the program as seal to a type variable x, or no seal, or seal to another type variable y, for example. Yes, it's possible.
Okay, thanks.
Hi, really nice work. I'm wondering whether your prototype implementation yields any insights into implementation costs of the possible sealing mechanism.
Sorry, could you?
Implementation costs. So the fact that you have this uncertainty in whether something is actually sealed, does that make it more difficult or more expensive to implement, or is it similar to implementing prior sealing mechanisms?
Yes. This work is completely theory. We don't evaluate a practical implementation. We have this prototype, but we don't experiment about efficiency or yes. But it's an open question if we can implement this formalism in an efficient way.
Thanks.
Thanks for the talk. So my question is about like slide 26, where you have like an example that seems like a bit, like intuitively, it seems like a bit weird to me in the sense of maybe you could make the case that if it one time is being used as X, then it shouldn't be able to be used as Y anymore. Could you do like other design decisions where you don't allow this? Or have you thought about this?
Sorry, could you?
So in this example, you something gets used as X and as well as Y. Could you make like the design choice that if you unseal as X, then later you can't anymore unseal it as Y?
Yes.
Related. It's not exactly the same.
It's exactly the same.
Oh, it's not
It's not
exactly the
exactly.
same.
Yeah, I guess just the question is, have you thought about, like, is this also a valid design decision to make, and whether, or like whether it's like an interesting other design perspective maybe, or?
Yes, it was not a decision of design, but it's something collateral that and don't violate any of the property of parametricity of graduality.
Okay, thanks.
Yeah.
I have a kind of naive question. Does any of this work sort of extend naturally to richer calculi, like with F omega? I mean, or pure type systems in general, or are we restricted to just plain polymorphism? Is that something that you or anyone else is thinking about?
Could you repeat if we can apply this plausible sealing to other?
F omega, for instance.
No, we didn't think about it, but this yes will be nice research.
So do you consider Brehm theorem? So Brehm theorem. So like so if you have Brehm labels, then you can find positive labels and negative labels when calling. Do you know Brehm theorem? Brehm theorem. Do you know Brehm?
Okay, blame there. No, we hear it on.
Yeah, is it possible to support a prove a Brehm theorem in setting? So
It's impossible.
impossible.
I don't know. We
Not-
didn't work in this with planes in this.
Not checked.
Ah.
Don't consider. You don't consider yet. Brehm. Yeah.
No. Yes, we in the paper in us we say that it will be nice to add plane to the calculus.
Great, that's not good.